Welcome to Lab 2. The aim of this experiment is to observe the motion of a free-falling object that is dropped from rest. The main physics principle that is being used in this experiment is Newton's second law, or equivalently, the momentum principle. The object that was chosen for this experiment was a crumpled piece of paper. To record the motion of the crumpled piece of paper, we have used the following video. We have taken the origin of our coordinate system as the approximate center of the crumpled piece of paper, and the negative y-axis is the downward direction in which the crumpled piece of paper is being dropped. The mass of the crumpled piece of paper is 5 grams and its approximate diameter is 11.5 centimeters. All these units are taken in SI units while performing calculations. The graph on the right depicts the y position versus time graph. The reason for a slightly parabolic graph is due to the presence of a constantly increasing velocity and a constant acceleration, which is due to gravity. Newton's first law states that the position versus time graph will be a straight line if there is no net force acting upon the object. However, here we can see that the graph is not a completely straight line, which is why we can say that there is a net force acting upon the crumpled piece of paper. These are a few formulas that we will be using in our experiment. Using these formulas, we can perform all the required calculations and we can find out that there is a constant force acting on the ball of paper. The first model that we will be taking a look at in this experiment is the case in which gravity is the only force acting on the object. We do not take into consideration the drag force in this model. This is the glow script program that we are using for our first model. Here we can see that the initial position and velocity of the ball are 0, and Newton's second law is being used in order to find the final position and velocity of the ball. We can see that gravity is the only force acting in this model. We can run the program to see the output, and we can see that the graph of velocity versus time is constantly increasing and is a straight line graph, which shows that there is a constant force acting on the ball. Using a spreadsheet, we can plot the graph that we got from the tracker application and the graph that we got from the glow script program. We can compare both the graphs and see that the model position versus time graph has a parabolic curve as there is a constant force acting on the object. This force is due to gravity. The experiment position versus time graph differs because it is influenced by drag force as well. Drag force acts in the opposite direction of gravity. In our second model, we will be taking drag force into consideration. This is the glow script program for the same. Here we can see that the drag force coefficient is 0.0071. In this code, we can see that the drag force is being added to the force due to gravity to find out the F net. We can run the program to see the output. Here we can see that the graph is quite similar to the tracker experimental position versus time graph that we had obtained earlier. This is because in both the graphs we have taken into consideration the drag force. This is what we obtain if we plot both the tracker application and the glow script program graphs on one single graph using a spreadsheet. This is a graph consisting of all the three graphs that we had plotted earlier. We can see that the model graph consisting of both gravity and drag force is much more realistic as compared to the model graph consisting only gravity. Before we answer the final two questions of the lab, it is important to know what terminal velocity is. Terminal velocity refers to the steady or constant speed achieved by an object that is falling freely. To answer the first question, we have to take into consideration the velocity versus time graphs for both our models. In the first model, we can see that the velocity is constantly increasing and terminal velocity is not obtained. In the second model, we can see that the velocity starts to become constant towards the end and terminal velocity is obtained. In this model, drag force and gravity have both been taken into consideration, and this shows that the net force towards the end when terminal velocity is obtained becomes 0. The final question requires us to study the effect of a change in initial velocity on the terminal velocity. On the right in the graphs, we can see that if initial velocity is changed, terminal velocity still remains the same. The only difference will be that if initial velocity is greater, the terminal velocity will be obtained faster as the object will require less time to accelerate. If initial velocity is even greater than the terminal velocity, then drag force will become greater than the force due to gravity, which will lead to deceleration till the time terminal velocity is obtained. This can be seen in the final graph when initial velocity is minus 3 meter per second. Conclusion: Newton's second law can be used to predict an object's motion. The model graph containing both gravity and drag force is more accurate and realistic, and terminal velocity does not change with change in initial velocity. Thank you for watching.